Hello and welcome to this webinar series, Harnessing NISAR Next Generation Radar Observations for Earth Applications. I'm Erica Podest. I'm a scientist at NASA's Jet Propulsion Laboratory, and I'm also an instructor with the ARSET program. Today's session will focus on the use of NISAR's InSAR capability, that's Interferometric Synthetic Aperture Radar, to monitor earthquakes, volcanoes, and landslides, which will be delivered by invited expert Dr. Eric Fielding from NASA's Jet Propulsion Laboratory. This is a training outline. Today is the third and last session of this three-part webinar series. There is a homework associated with this training, and it can be accessed through the training webpage. The due date for the homework is August 6th, and a certificate of completion will be awarded to all of those participants who attended all three sessions live and complete the homework assignment by the due date. How to ask questions? To ensure we see your question, please write your question in the Q&A box, which you can locate it by doing a click on the three dots in the bottom right of your of the window in the platform. And there you'll see a Slido, a Q&A option, and you can also see a standalone Slido tab or app. Write your questions or all your questions there, and we will answer them during the Q&A session at the end. And we will try to answer all the questions during the Q&A session. The remaining questions will be answered in the Q&A document, which we will post on the training website about a week after the training. Today's guest instructor is Dr. Eric Fielding, who's a research scientist at NASA's Jet Propulsion Laboratory. He's a geophysicist and an expert in the use of radar interferometry, or InSAR, for studying tectonic movements, landslides, and other phenomena. Dr. Fielding is also part of the NISAR science team. He's a globally recognized expert in the use of InSAR and has supported many or all of the InSAR sessions that ARSET has offered. So I'm extremely grateful for his involvement today as a guest instructor in this training. Welcome back, Dr. Fielding.
My name is Eric Fielding. I'm a geophysicist at the Jet Propulsion Laboratory, operated by the California Institute of Technology in Pasadena, California. Today, I'm going to be talking about how NISAR can be used to monitor geologic hazards, including earthquakes, volcanoes, and landslides, using the InSAR capability of NISAR. Here's the overview, what we're going to cover. Interferometric SAR, or InSAR, measures the displacement of the surface. We're going to concentrate in this part on the geologic hazards. Earthquakes, volcanoes, and landslides are the main ones. And I'm going to be showing this image on the right here is just a eye candy image of the interferogram for the volcanic eruption of this volcano in Ethiopia called Haile Gubi that erupted in November 2025, fortunately just after NISAR was ready to start collecting science data. The prerequisites for this training are the fundamentals of remote sensing training. The prerequisites for this training, assuming if you have no background, would be to follow these previous ARSET trainings on fundamentals of remote sensing. There was one on SAR processing and data analysis in 2017, and a more extensive introduction to SAR interferometry in 2017, or some other equivalent experience in understanding SAR interferometry. I'm going to give a summary here, but not all the details. And then, of course, the 2 previous sessions in this series. Okay, so I'm going to be covering now the how SAR interferometry works. By the end of this training, you should be able to understand what NISAR InSAR products are and their characteristics, have some idea about the uses and limitations of InSAR data from NISAR, and see how we can use NISAR InSAR to study large displacements of volcanoes and earthquakes, and also how to use that InSAR to study more gradual displacements of landslides and other more slow-moving phenomena. So I'm just going to give a quick review of what was in that 2017 ARSET training on the SAR interferometry theory. In SAR interferometry, the key thing is the phase of the SAR signal. And in many other applications, for mapping vegetation or floods or biomass, those use the radar amplitude, SAR amplitude, but we're going to be using the phase of the SAR signal. The SAR phase is a measure of the range between the satellite antenna and the ground, plus something about the complexity of the objects within a given radar pixel. Because these objects are essentially randomly located within the pixel, the way that we separate those random effects from the actual measurement, which is the range from the satellite to the ground that we want to measure, by using SAR interferometry or differencing of the radar phase. So this is just a simplified version of the SAR phase. We have a phase observation phi1, which is equal to 4 pi over the radar wavelength lambda times the range rho 1 plus other constants, which are those distribution of scatterers within the pixel, and then plus n1, which is noise, system noise. And then for the second image, which is phi 2, again, we have the same constant at the beginning, 4 pi over lambda, the radar wavelength, times the range of the second acquisition between the satellite and the ground, and other constants, which we are going to assume are the same. And then there's some noise, which we hope is small. Because these other constants can't be directly measured, what we do is use SAR interferometry to basically we subtract phase 1 from phase 2, or phase 2 from phase 1, to cancel out those other constants. This is a simplified view of what we're looking at for what we call differential interferometry, where we're trying to measure the displacement of the surface. If we're lucky to have our 2 satellite passes exactly the same location, then T1 and T2, at T1 and T2, the 2 antennas are in the same place. And then the range at T1 and the range at T2 can directly measure the change in range, which is what we want to measure. Again, we get this, we want to look at this change in phase, which is then proportional to 4 pi over lambda times the change in range, rho. Another key aspect of SAR interferometry is that we can only measure the radar phase modulo 2 pi. Basically, the phase is going around in a circle, and it's in the complex numbers, and we can only measure the phase modulo 2 pi. So this top graph here shows the actual phase that we want to measure It's the distribution of phase across a line across the interferogram. And after we do the measurement, then we end up with this wrapped phase where all the values are between minus pi and plus pi. And we can see then we have these discontinuities where it suddenly goes from minus pi to plus pi, and there's several of these discontinuities here. And that's what we call the wrapped phase. And then what we do in the processing is use a computer program that's specialized for doing what we call phase unwrapping. It tries to go through the whole image and figure out where these discontinuities are and how to reconnect them and get back to the original phase. Although the the unwrapped phase will be different from the original phase by some arbitrary constant that we will have to deal with later. These other equations here we're not going to go into in detail, but there is some, for pairs of satellites where there's some difference between the two antenna locations, there's also some phase that's due to topography, and we will subtract that out by knowing the topography. Another key aspect of SAR interferometry is that it's there's a coherence, and that's basically a measure of that noise term that we had in the first equations, where there's some amount of noise in the phase 1 and phase 2 measurements, and if that noise is high, then the coherence is low, and if the noise is small, then the coherence is high. In the past, many people have used the word correlation because this coherence is measured by the correlation of phase between adjacent pixels. If you look at papers from a decade ago or more, you almost always see the word correlation. But in the last 10 years, people have started using the word coherence for this measurement. It's really the same thing, but they are all the recent papers and the InSAR products from NISAR use the word coherence. So the key things that cause this noise are thermal and processor noise. This is generally very small. Differential geometric and volumetric scattering. This is where the radar waves are bouncing off of a volume of scattering objects. Typically, this is a forest where the radar may be bouncing off different layers in the forest. And that's heavily dependent on the radar wavelength. Another thing that can cause noise is the rotation of the viewing geometry with modern satellites. That's not a concern. And then there's the issue of random motions over time, which are maybe a tree fell down or a rock rolled down the hill or there's a landslide that completely disrupted the hill. So these are examples of the types of things that cause a loss of coherence or what we also cause decorrelation. And we can relate this coherence or correlation to the standard deviation of the phase, or it's basically an estimate of the standard deviation of the phase. So that affects how accurately we can estimate height from InSAR. There are ways of using InSAR to measure elevations, although not with the NISAR satellite, or displacements, which we're going to be talking about here. And the loss of coherence, if the coherence is low, then that also affects our ability to unwrap phase, because it's more difficult to know which phase jumps need to be connected. So now I'm going to be talking about the NISAR InSAR data products and their characteristics. So this is a simplified processing diagram for the NISAR system. The NISAR processing system, level 0A is the data that comes down from the satellite that gets reformatted and with additional information becomes level 0B. These are the raw data products, not usually used by regular users, although some power users do their own processing with the level 0 data. That's then processed into level 1, which is in radar coordinates. The R here means radar coordinates or range Doppler coordinates. The RSLC is the range Doppler single look complex image. This is then the key product that's used to make all the level 2 products. The level 2 products are all in geographic coordinates, so they're geocoded. The first one is a geocoded single look complex image. This is a new data type that is, as far as I know, not been produced by any other satellite mission, although the Opera project at JPL has been reprocessing Sentinel-1 data to a similar product that they call the co-registered SLC, co-registered single look complex, as a post-processed from the original ESA data products. It's a range Doppler SLC. There's a geocoded covariance matrix, the GCOV. That's the amplitude images with radiometric terrain correction that's used by ecosystems and other studies of the radar amplitude. And then there's these two types of interferometric products, the geocoded offsets, which are used for cryosphere, or the very large motions of ice, and the geocoded unwrapped interferograms, the GUNW, with this red circle here, which is what we're going to be talking about today. That's the useful for solid Earth and the parts of the cryosphere that are not moving so fast. And these other boxes here show the intermediate products that are used in the processing, where that to make the final geocoded products, there's a range Doppler offset field, a range Doppler interferogram, a wrapped interferogram, then that's unwrapped to a range Doppler unwrapped interferogram, and that's finally geocoded to make the geocoded unwrapped interferogram, the GUNW. So the NISAR level 2 GUNW file it's an HDF5 file like all the other NISAR products, and it has multiple layers inside of it. So these are some of the key layers. There's an unwrapped phase layer. That's the actual unwrapped phase. It's at 80 meter resolution. Looking down to below that, we have the interferogram coherence. That's also for the unwrapped phase. That's also 80 meters. Then there's a wrapped phase. They actually include the wrapped interferogram within the GUNW file at a much higher resolution. This is at 20 meters pixel spacing. And the wrapped interferogram then has these individual color contours that are all of the phases between minus pi and pi that repeats across the scene. And another key layer is the ionospheric phase. In this particular slide, we've taken the ionospheric phase is normally unwrapped. It comes as an unwrapped phase at 80 meters, but it's been rewrapped here just for a better comparison to the wrapped phase, which shows that almost all of these fringes in the wrapped phase interferogram are due to the ionosphere. And that's one of the key things about SAR interferometry with the NISAR L-band radar instrument. L-band has a 24 centimeter wavelength, and it's much more sensitive to the ionospheric effects than shorter radar wavelengths. So the ionospheric phase is a key thing that we're going to need to subtract for most of the types of analysis that we do. The other two panels here show a solid Earth tide, which is the people are probably I'm sure familiar with the tide of the oceans, but it turns out that the gravitational attraction of the The moon actually also causes the solid Earth to flex somewhat, and that can have a small but a measurable effect on the interferogram. So we include a calculation of that in case you want to remove this this small but easily determined effect. And then the other another layer is the tropospheric phase. So the ionosphere is a part of the atmosphere that's very high above the Earth, over basically over 100 kilometers. And the tropospheric phase is the lower 15 kilometers where we all live and where most of the water vapor is. And that water vapor actually causes an effect on the propagation of the radar waves. So we also include an estimate of what the tropospheric phase is from a weather model provided by the European Center for Medium Range Weather Forecasting. So as written down here, the unwrapped phase and coherence and the ionospheric phase are stored at 80 by 80 meter pixels. There's a water and subswath mask also at 80 meters. There's the 20 by 20 meter pixels of the wrapped phase, and then there's also a wrapped phase coherence layer that also has that 20 meter pixel size, much higher resolution than the wrapped into unwrapped coherence. And then there's these the tropospheric delay and solid Earth tide are actually stored as 3D cubes, which is a little bit complicated to explain and more advanced topic. And the range Doppler interferogram and range Doppler unwrapped interferogram are only saved and stored in the archive for over cryosphere regions, some areas of Greenland, Antarctica, and other major ice sheets. So this is sort of a review from the session 2 from the ASF folks about how NISAR data are stored in the NASA Earth Data System. The Earth Data System is hosted in the Amazon Web Services cloud. Earth data can be searched directly from the Earth Data search tool at this URL. Find that not as easy to use as the more specialized search tool at the Alaska Satellite Facility, ASF, that's specifically designed for searching for SAR data, including NISAR. So I'll be showing how to use that. Heidi also showed that in her presentation, but I'll be showing it just specifically for GeoNW data. So you can download either one of these user interfaces, and it's the same data. It's just the user interface is different. The ASF guide to NISAR data download usage and tutorials is excellent, and I highly recommend going to the NISAR docs.asf.alaska.edu page to find out more information about how to do the downloads and various usage, and they have some tutorials there. At the time that I created this presentation in June 2026, we only have a limited set of uncalibrated data that were released publicly in February, and that's what I'm going to be showing today because that's what's available now. The planned release of the calibrated data is in July, and this part of the ASF NISAR docs page shows the updated release timeline, which they update frequently, so you can see what most recent timeline is for the big calibrated data release in July. So I'm going to show here how to search for the GeoNW, geocoded unwrapped interferograms, through the ASF search tool. Usually if you go to the search tool, it comes up with the data set set to NISAR automatic as default, but if it's not, then you have to choose NISAR. You draw a box around your area of interest. This is an area in Ethiopia where that volcanic eruption happened in November 2025. I just drew a box around the two volcanoes. There's Erta Ale volcano and the adjacent Haile Gubi. The eruption actually came out of Haley Gubi, but there was additional deformation underneath Urta Ale because the magma drained out of Urta Ale and went into the Haley Gubi volcano. So once you've selected your box, then you can add a search filter with the filter button at the top of the page, and go down here, choose Science Product GONW to only get the geocoded unwrapped interferograms. You can also choose a date range if you only want to see certain dates here. And this is the result of that search for the GONW files over the Haley Gubi and Urta Ale area in Ethiopia. One of the key things, of course, is we're talking about interferograms. So the interferograms have two dates, the before date and the after date. In the list here, the interferograms are always listed by the first date of the pair. And because we're trying to see this eruption that happened on November 23rd, we choose this interferogram that has the first date on November 22nd, and then which then has a second date 12 days later on the December 4th. And so that's on the left here, you choose the specific scene, and then in the middle here, it shows details about that scene. There's a very complicated naming convention here, but the ASF interface shows the key pieces of information down here extracted out of that name, the start time of the first date, the stop time of the second date, the track number, the frame number. It's an ascending track. This frame is a full frame. The interferogram polarization is HH, that's horizontal transmit and horizontal receive. And the range bandwidth, which determines the resolution, is 20 megahertz. And then there's this CRID, that's the composite release ID that tells you the specific version of the software that was used to create that product. This is from the preliminary release of February, and it's CRID X5010. The release in July is going to be P05022, and that's how you know the difference between the what processing version. So then over on the right side, you get the list of the actual products for that scene. There's a list of products. Probably Heidi covered this. The top one is the level 2 GONW HDF5 file. That's a large 2 gigabyte file. But there's also other files here. You press this little download button to just download. If you have not logged into Earth Data in this session, then you may have to log into Earth Data again. But there's also some other items here that are useful to download. There's a browse image. That's the image that actually shows in this lower part of this center panel. If you scroll down, it's an overview of the phase of the whole scene. There's a QA report that has a number of images of all the different layers, and those two can be used to make sure that the scene covers the area you want to cover without having to download that big 2 gigabyte file. And then it's not visible here because I haven't scrolled down in this slide. There's another file called the footprint KML. By combining that footprint KML file with the PNG, then you can visualize it in Google Earth. This is just an image taken from one of the pages of the QA or quality assurance report. These reports are available for all NISAR level 1 to level 3 products. First page has basic metadata data about the acquisitions. And then the other pages have these types of maps or graphs of histograms. On the left here is the full unwrapped phase. You can see it goes from -10 to +30 radians. That's much more than the minus pi to pi. On the right here, what they've done is taken that unwrapped phase and rewrapped it to the range between 0 and 7 pi. This is what the data in the February release showing. The new data that's going to be processed and available in July will have a wrap at the rewrapping at 0 to 2 pi, which is a little bit different. And there's similar pages for all the other layers. So this is what the browse product looks like if you take that PNG image and the KML and put them in the same directory and double click on the KML file. It should be able to load into Google Earth if you have Google Earth on your computer, or you can also load it into Google Maps. It's a very convenient way to see the coverage of the scene. The Haley Gooby area is this corner near the edge of the scene. As I mentioned before, this is the 7 pi wrapped phase, and the final products will have a 2 pi rewrap of the phase, which will make it look considerably different with more fringes. So now I'm going to talk about some of the uses of the NISAR InSAR data, using some examples from previous satellites, since we don't yet have a lot of good examples from NISAR. This is a map that was made more than 20 years ago of volcanoes in the central Andes of South America. And Matt Pritchard, who was then a student but is now a professor at Cornell, made this map and found that there were significant InSAR signals over many of these volcanoes in the central Andes. Some of these signals were over volcanoes that had known recent eruptions, but other of these volcanoes did not have any known eruptions and weren't even known to be active. But the InSAR here then showed that these were having some amount of displacement and deformation at depth and had to be considered active. This is a more extreme event that happened also in Ethiopia and in a part called the Assal Rift. There was a huge injection of magma into a shallow fissure that opened up. The two sides of the fissure spread apart by more than 5 meters. These are people along the edge of the fissure, but for scale. We can see that this wide fissure is basically the line here at the middle of this interferogram, and all these fringes show the displacement of the ground surface away from this dike that was intruded into the crust here in East Africa. And this happened in 2005. This is an example of an earthquake that I studied with some other people that happened in 2015. It was a magnitude 7.8 that happened. It started at the location of this star here in an area near a town called Gorkha in Nepal, but it then propagated far to the east, past Kathmandu, and into almost to eastern Nepal, a distance of over 200 kilometers. And so this map here is made from ALOS 2, the Japanese ALOS SAR satellite called ALOS 2, which is also an L-band system. It was launched in 2014, and it's now being moved to retirement because it's been replaced by a new satellite of JAXA's called ALOS 4. But in 2015, it had just started operations, and it got this excellent image of the Gorkha earthquake. I show here the line of sight direction. As I mentioned earlier, what we measure with InSAR is the displacement in the range direction. That's also normally called the the line of sight between the satellite and the ground. So a lot of times you'll see this LOS or line of sight arrow showing the horizontal projection of that line of sight. But that line of sight also has a vertical dimension, which is because the satellite's looking down at the ground. And the INSAR only measures displacements that are parallel to that line of sight direction. And for this specific earthquake, we have these GPS stations that were being operated in Nepal. The triangle here shows the location of the station, and the arrow shows what direction that GPS measured the ground displacement. And you can see that ground displacement is almost perfectly perpendicular to the line of sight. And that means that we're basically not able to measure that horizontal motion because it's perpendicular to the line of sight and the horizontal component of the line of sight. And what we can measure is the vertical component. This earthquake was a thrust earthquake. And that means that the area of the Himalayas was thrust to the south, and part of that resulted in uplift in this area of red, including the city of Kathmandu, and the area further north in the high Himalayas was actually dropped down as much as 1 meter. There's one little extra weird thing here that's kind of a extra complication. But we're only seeing the vertical component of this particular earthquake. In other cases, the radar line of sight here, usually if you see a symbol like this, the longer arrow is the direction the satellite was moving, and the smaller arrow is the radar line of sight direction. In this case, the line of sight is west and down, but we're looking at displacement along this central part of the San Andreas Fault in California. And this particular part of the San Andreas Fault moves continuously at almost the full rate. So we can see after a few years this large area of discontinuous motion across the fault, showing that the fault is creeping or moving aseismically. And that this particular section between Parkfield and San Juan Bautista, the central San Andreas, has this creeping or aseismic slip that we believe means that while it may have some small earthquakes, maybe up to magnitude 4, it's not going to participate in large earthquakes. And it acts to separate the northern part of the San Andreas to the northwest, which is the section that ruptured in 1906, from the southern part of the San Andreas Fault from Parkfield to the south that last ruptured in 1857. Another thing that we can use the INSAR for is looking at surface changes. As I mentioned earlier, coherence or correlation measures the change, the noise in the radar between the two dates, and that can be affected by both vegetation or major changes in the surface. This is a paper that I wrote 25 years ago. So, of course, at that time I used the word interferometric correlation, which is the same as what we now call coherence. And in this particular case, there was this horrible, devastating earthquake in the city of Bam in Iran at 6.5 in December 2003. This was just after the Envisat satellites started operations, so we were able to get this Envisat interferogram, and one of the things we noticed when we first made the interferogram is that the correlation or coherence had this line extending south from the city. The geologists there in Iran were trying to find where the fault rupture might have been. We sent them this map, and they were able to go to the field. This was basically a desert area that nobody ever went to, and find these surface ruptures marked by these circles at the locations where there was this decrease in the coherence in the interferogram. And then we took this a step further and looked at the change in coherence. If I go back, this particular, the city of Bam, it was mostly, is the main population center and largely houses with some vegetation between some of the houses. But then there was an adjacent town over here called Baravat. And this is almost entirely date palms. So it's vegetation. And this low coherence over Baravat is due to vegetation, whereas a lot of this low coherence over BAM is due to actual destruction of the buildings. And so by taking the interferogram that includes the earthquake, the coseismic correlation or coherence, and subtracting the coherence of the another interferogram that we made for a pair before the earthquake, then that subtracts out the effects of the vegetation. So Baravat is now approximately 0, and these red areas in the city of Bam show the extreme destruction of large parts of the city, and the fault ruptures going south are very clear in this red color. And we also found that there was an additional fault rupture north of the city. So this is what we call coherent change detection or correlation change. And that's another use of interferometry, is to actually use the coherence as a measurement of surface change and possibly damage to buildings. The fault rupture was down here to the south, and it ruptured towards the city, which really focused the energy into the city and caused this horrible devastation. I think over a quarter of the population was killed in this unfortunate earthquake. So landslide motion is another application of SAR interferometry. This particular interferometric SAR map was made with a airborne radar system that NASA owns, it's called UAV SAR, but it actually flies on piloted Gulfstream airplanes. And that radar was built at JPL, and it flies on the piloted airplanes out of NASA Ames. That also uses L-band like NISAR, so this is sort of a preview of what NISAR is showing, but using the airborne system. The airborne system, because it's closer to the ground, can have much higher resolution, so it's not quite the same, but it gives an idea of how we can measure these very high displacements. This particular landslide has a central section here that moves over 2 centimeters every day. And I'll be showing another example a little bit later in Los Angeles, moving almost this fast. So one of the things to think about is what are the limitations on INSAR measurements. So we observe a phase here, the phi observed, and it's actually the sum of all these other effects. There's the line of sight displacement, which is what we want to measure. As I mentioned earlier, there's some amount of phase that comes from the troposphere. There's some amount of phase that comes from the ionosphere. There can be some phase that's due to inaccuracies in the DEM that you're using, for the processing. And then there's this noise term, which is basically that decorrelation. And so these phases are added together. I mean, the noise is random, so we can't subtract it out. In the ionosphere, we have an ionospheric correction layer in NISAR and a tropospheric correction layer in NISAR, so we can subtract out both of these effects and get back the line of sight displacements that we want to measure. The coherence effects are multiplicative. They're not like the phase effects that are additive. And that means that any one of these effects, if any one of these different effects are low, then the resulting multiplied coherence is also low. It also means that we can't just subtract out one effect because they're multiplied together and not added. And in this particular separation, I've separated out the volumetric coherence to trees. There's also some amount of effect of loss of coherence due to steep slopes. There's a coherence change that's gradual, like plants growing, or that's one of the typical ones. And then there's a correlation loss due to sudden changes, like landslide disruption or the disruption of an earthquake. So these are the key components of the coherence. So now I'm going to be talking about two case studies for how applying some NISAR InSAR data to volcanoes. Because I want to have this accessible to everybody right away, I'm going to be using data that was released in that February release that's already at the ASF and Earth data repositories. During the time of that's included in that February release, there were no earthquakes with significant InSAR signals. So I'm not going to be able to show you an earthquake example. So we're going to be looking at this volcanic eruption in Ethiopia that's part of the East African Rift System. As I mentioned earlier, there's these two volcanoes next to each other. The Orta Ale volcano has been very active for decades and has had a lot of eruptions. And then an adjacent volcano called Haley Gubi had not been active and in historic time, and there are suggestions that it hadn't been active for as much as 5,000 years, although obviously we don't have 5,000 years of recorded history. It's part of the East African Rift System, where the eastern part of the African plate is pulling apart. That gives this extensional stress to the rocks there. And this Haley Gubi volcano erupted suddenly on the 23rd of November without people really expecting it. What we can see in the interferogram is that, in fact, the magma drained out of the Orta Ale volcano, and the Orta Ale volcano actually had a dike that contracted, and that magma then moved into Haley Gubi and erupted in a quite explosive eruption that spread ash over a large area, and it even sent ash into the stratosphere. So there were ash clouds that blew far to the east after this eruption. So first, I'm going to show you some slides with wrapped interferograms that were generated by Matt Pritchard, who's at Cornell, as I mentioned. He's still looking at volcanoes since he's been a grad student, and he made these slides. These maps are just for a small subset of the full NISAR frame. So Matt went back and looked at, there was one NISAR interferogram for the 12 days before the eruption. And in fact, we can see this is a wrapped interferogram, so the phases are minus pi to pi, which we can approximately convert to surface displacements between 0 and 12 centimeters. There was a small amount of displacement here in the Haley-Gubi volcano. Probably the magma was starting to move into the volcano before November 22nd. And there was some indication that this dike underneath the Erta volcano had started to close or contract. So a little bit before the eruption, there was this precursor, but nobody had seen this because they hadn't thought to look at it. And then the next interferogram is the interferogram that includes the eruption. As I mentioned, the Haley-Gubi eruption it sent a huge amount of volcanic ash out, and ash and other larger rocks are called tephra by the volcanologists, and that tephra has covered up the land surface and made it completely different from the two radar images, and that's why we see this area of low coherence or noise in the wrapped interferogram. And there's a slight hint of some possible deformation just to the west of the main Haley-Gubi volcanic peak that is still being studied. And then this is the signal over the Erta volcano, and what we see here, this is actually sort of the opposite of that dike intrusion that I showed from the one in the Asal rift. And in this case, the two sides of the dike moved together because the magma actually drained out of the dike during this and moved into Haley-Gubi. And so this is the wrapped interferogram. I'm showing these here because the demonstration I'm going to show is with the QGIS program, and the QGIS program cannot show the wrapped interferograms. And then this is the radar track angle. It's an ascending track with the radar looking to the west, to the left. So you probably heard in the previous session about how NISAR data are stored in this HDF5 format. The HDF5 files are a version of what's called NetCDF. The ArcGIS package can read the NISAR HDF5 files directly, but we're going to be using GDAL and QGIS. The QGIS is an open source and free and open GIS program. It's available for a wide variety of platforms, whereas ArcGIS only runs under Windows. And the present version of GDAL needs to be told that this HDF5 file should be read with the NetCDF driver in GDAL. And because QGIS uses GDAL, we also need to do that for opening it in QGIS. So there's two options. We can actually rename the file, take the .h5 file that we download from ASF or Earth Data and change it to be .nc for NetCDF. That's the preferred option. You can also add this NetCDF colon to the front of the file name. And that allows you to open it when you're opening the file in QGIS, but that actually doesn't work very well in QGIS, but for doing additional processing steps. So I recommend, if you're going to open in QGIS, to use this renaming option. But this NetCDF colon can be used for doing other GDAL operations that you can do from the command line or other ways. And as I mentioned earlier, the QGIS cannot display the wrapped interferogram layers in the GONW file because those are complex numbers, and QGIS doesn't know what to do with complex numbers. I'm going to stop here and go to QGIS. Okay, so I've already I pressed the load raster dataset button. The load dataset, I've selected raster here. I'm going to go to the this directory. You can see here is my GONW file. I've renamed it as .nc. So now I can open it directly in QGIS. When I press add here, it shows me all the possible layers that are inside this GONW file. I don't want to load all those files, all those layers. I'm just going to load the coherence magnitude, ionospheric phase screen, uncertainty, the unwrapped phase, the mask, and the wrapped interferogram coherence magnitude that has that 20 meter resolution. So this is it opens this, it actually loads it into QGIS as a group of layers, all those layers from the same interferogram. I'll just turn off all the layers but the coherence first, so we can look at the coherence. Okay, so I've turned off all the layers except for the unwrapped interferogram coherence. And now I'm going to zoom to that layer. This is the coherence for the whole scene. And you can see this is a desert area, so the coherence is very high almost everywhere. Coherence is a normalized number. It goes basically from 0 to 1. And there's large areas here which are very close to 1 in this dry area with very little vegetation. There's this basically zero coherence in the top right corner. That's the ocean of the Red Sea adjacent to the land here. Water always has basically zero coherence because the surface is completely different 12 days apart or even an hour apart. And there's another water body here. I'm not sure what the name of that lake is. And then there's some areas here that have sort of intermediate coherence values. And those are areas that probably have some loose sand. And sand is one of the things that can cause, if there's a large amount of sand at the surface, can cause low coherence just because it absorbs a fair amount of the radar and reduces the amount of signal sent back. But also in a lot of desert areas, the sand can move around, and there also cause a lower coherence. And then we can see this sort of spot up here, and that's the area of the Haley-Guby. This big blob here is the low coherence of the Haley-Guby eruption and ash flows, and then there's an area of the Earth-Ale that where the displacements are so large that the coherence gets lost. One of the rules of InSAR is if the displacement within the radar pixel size is more than half of the radar wavelength. So with NISAR, that's 12 centimeters. So if you have a 12 centimeters within the 80 meter pixel of our interferogram, then you'll lose coherence and not be able to make a measurement. this is the unwrap phase. One of the things I always do when I load the unwrap phase is go into the band rendering and change it from a grayscale to a pseudo-color. I usually use this color ramp from red through white through blue, and that gives this. Now we can see clearly that the two sides of the dike in Urtalli moved in opposite directions. We can also see that the area of Haley-Guby is basically pure noise. And we can go back into that and change the color scale. This is still in radians. It's unwrap phase, -20 to +20 radians. The displacements are larger on the east side of the dike than they are on the west side of the dike. And that's because we're measuring these displacements in the radar line of sight. The line of sight of this track is down and to the west from the satellite to the ground. Blue means it moved away from the radar, and red means it moved towards the radar. And that means that the two sides move towards each other. And that's because this dike is contracting, because the radar moved out, the land moved out. And because, so on the east side here, the ground is moved away from the radar, both horizontally towards the dike, but it also moved down as part of the displacement due to that withdrawal of the magma. And because the westward and the down motions are both in the same direction relative to this radar line of sight, those two are adding together, and we get a larger signal on the east side here. And on the west side, the ground motion is to the east, but the ground moved down. And that means that the horizontal motion is towards the satellite, but the vertical motion is away from the satellite, and they've tended to partially cancel out. And that's why the displacements on the west side are quite a bit smaller than the east side. So that's the interpretation of this dike collapse or contraction. Earthquakes have a very similar type of pattern. You'll have you're always measuring this combination of the horizontal and vertical displacements. So you'll see a similar. You have to do this similar type of analysis of what displacements mean in the radar line of sight. And by getting a second radar line of sight, say this is the ascending track where the satellite was moving north. There was also a descending track over this area where the radar satellite was moving south. So that would then have the satellite looking to the east. And that would show an opposite pattern here, which would tell us that this has a large horizontal component. That descending track was not included in the February release, so I'm not going to show it to you here. But now I'm going to zoom out to the whole frame. This is the whole frame. And so the displacements there at Urtalli are quite large. But if we go back and change this color scale to be more representative of the whole scene, then we can see this is from -2 to +4 radians. We can see that there's this large kind of gradient of the displacements across the scene. and that's largely due to the ionosphere. NISAR ascending track scenes are acquired at approximately 6 a.m. local time, and that is when the ionosphere is less active. So generally the ascending tracks have less ionospheric effects, and the descending tracks are acquired at 6 p.m. local time. And that is a time when the ionosphere is much more active. So you'll see in many places that there is a descending track interferogram that has many more ionospheric effects or fringes than the ascending track for even the same location. And it also depends on latitude. The ionosphere is much stronger near the equator. This is quite near the equator in Ethiopia, and they're less at middle latitudes, and then they're very strong again near the poles. So looking at Alaska or other high latitude areas, you'll see that the ionosphere is even more extreme. So we're going to just take a quick look here at the ionospheric phase screen. This is the, and one of the tricks I can use in is, well, I'll use the same pseudo color. I'm going to set this to 2% count. And we can see now that the ionospheric estimates are generally are generally close to zero for this scene. But if this was a descending track scene, we'd see a much stronger effect. So this particular scene is not a good example to show for the ionospheric phase screen calculation. This was processed with the older version of the NISAR software, and it has these blue areas are places that had that low coherence, and the ionospheric estimate is with that old software ends up with bad values in those areas of low coherence. That's been fixed in later versions of the software, and we'll see that the ionospheric estimates for more recent that are going to be released next month or in July will have much higher quality and not have these kind of weird patterns where there's low coherence. One other thing I just wanted to give a quick look at is the wrapped interferogram coherence. Turn off these phase layers. So this, we go back to Haley Gooby here. This is the coherence layer from the wrapped interferogram at 80 meter pixels. And if we turn that off, we can see the coherence layer from the wrapped interferogram, and this has 20 meter pixels and shows you much greater detail. There must be some kind of a tongue here, of maybe a valley where the ash has moved down the valley here. So we get much more detail in the coherence of the wrapped interferogram layer. So the QGIS can display the coherence from the wrapped interferogram, but it can't display the phase from the wrapped interferogram. So that's why I showed you the slides. So that's our example of a volcanic eruption, and it's similar to earthquakes. And now I'm going to go back and show you a landslide example. So landslides are a major hazard in many places. We have a lot of landslides in California, and they're also important process in many mountainous areas, but they can occur even in relatively mild hilly areas in a wide variety of locations. The amount of impact of landslides depends on their specific location. And we're going to be getting this NISAR data to be able to map landslides worldwide. I'm going to be talking today about a specific landslide in an area called Palos Verdes. This is a city in Palos Verdes called Rancho Palos Verdes, where a landslide accelerated in 2023 and went right through the edge of the landslide, went right through this neighborhood, including this house right here. This is the vertical view. You see this landslide edge here that went right through the middle of this house and completely tore it apart in 2023. This house has now been was red tagged. That's the U.S. Equivalent of condemning the house. It's saying it's no longer useful for human occupation, and it's now been torn down. But these other houses nearby, a lot of them had only what we call a yellow tag, which means that the owners could actually still go into them. Some of them they've been trying to put some like supports underneath the house to try to keep it from sliding down the hill more, and that's an ongoing situation here. These landslides are, as I mentioned, in Palos Verdes. Palos Verdes is this circle's in the wrong place. It gets shifted a little bit. Palos Verdes is this funny little peninsula that sticks out from the coast just south of Los Angeles. Downtown Los Angeles is up here. These two black lines here are the low coherence of LAX runways. These views here are a combination of the wrapped phase for these pairs and the coherence. That's one of the tricks that I often use is actually combining the coherence with the phase. I'll show you that in a minute. This Palos Verdes Peninsula is southwest of the main part of Los Angeles, and the southern west coast of Palos Verdes has this large landslide complex. Some parts of this landslide complex have been moving for about 60 years. Since actually the 1950s, almost 65 years. And that part was known to has been moving for a long time, but we had very heavy rainfall in 2023 and again in 2024, and that caused both those older parts of the landslide and other parts of the landslide to accelerate drastically. And cause the damage that you saw on that previous slide. At one point, it was moving at the rate of around 5 centimeters per day, even faster than that Slumgullion landslide that I showed earlier. That's based in Colorado. So these are wrapped interferogram results from the on the left here, the descending track, and on the right, the ascending track for an interval in between November and 12 days, November 23rd to December 5th. It turns out that just one day later, the ascending track, November 24th and December 6th. And you can see these two maps look very different. And that's, again, because we're measuring the surface displacements in this radar line of sight direction. The descending track, the line of sight is to the east, slightly south, and on the ascending track, it's to the west and slightly south. So the horizontal motions in these two look directions are going to have opposite signs, and the vertical motions have the same sign. If we look at this area in the upper left, it's blue in the ascending track, descending track, and in the ascending track, and that's because that area is moving downward. This is sort of the top of the landslide where the land is moving down and then out. And other areas here, the two measurements are in opposite directions, and that's because it's mostly we're measuring the horizontal motion. But again, we also have to remember that the big motion of this landslide is actually almost due south, and that's in the direction that's roughly perpendicular to the radar line of sight. So we're not seeing the big motion of the landslide southward, but we're seeing this vertical motion along the edges, and some parts of the landslide are moving west and some parts are moving to the east. And this is just the same. You'll notice that on this that it's actually hard to tell which is positive and which is negative, and that's one of the difficulties of interpreting unwrapped phase. And this is the same two interferograms with the unwrapped phase. Of course, it's 80 meter pixels instead of 20 meters, so we have a coarser resolution, but we can see which parts are positive and which parts are negative. Again, we have this upper part in the upper left corner, which is red or positive away from the satellite in both ascending and descending, and that's because it's moving down. And then there's this section in the southwest where it's positive on the ascending track because it's moving towards the satellite to the west, and it's negative on the descending track because it's moving to the west, which is away from the satellite on the descending track. Due to the way these particular tracks were acquired, they ended up excluding these particular scenes from the February release. So I'm only going to show you the ascending track data, which is in the February release. And now we're going to go back to QGIS and open the Los Angeles interferogram. I did the same process of downloading the GUNW from the ascending track for the area of Los Angeles, and this is after masking. So this is the unwrapped phase. Again, as we the ocean next to the peninsula is water, so the unwrapped phase is all noise. So one of the ways to hide that unwrapped the noise in the ocean is to go to this coherence map. This is the coherence map from the unwrapped phase, and make this particular coherence map set to multiply instead of normal. And now if we put the coherence map on with, let me turn off this Google satellite, with the unwrapped phase, now we get this this view where the low coherence of the ocean is black, and therefore easier to focus on the land part where the measurements are good. So this is the ascending track. So again, this has that area at the north part of the landslide that's moving away from down and to the west slightly, and this lower part there where it's also moving to the west. One of the other things I can show you with this interferogram is the whole scene. If we look at the whole scene and change the stretch of the interferogram, on this pair, we can see that there's a much stronger ramp from north to south, and that's due to the ionospheric effect on this pair. And if we go to the ionospheric phase screen layer, this is the phase screen layer. Let me turn off the coherence. We'll set that to be a pseudo-color. And let's turn this coherence back on. So now we can see basically the same pattern of gradient across the scene in the ionospheric phase screen. So by subtracting this ionospheric phase screen from the unwrapped phase, then we get a corrected interferogram that we can use to look at a larger area of the scene. So one of the other things we can see in this overview of the whole scene are these little patches of low coherence. These are in the mountains, the San Gabriel Mountains that are just north of Los Angeles. And these are actually areas of snow. This was a pair that's in the winter, and these higher elevations in the San Gabriel Mountains are covered with snow, and that's what's causing this low coherence in these in the high parts of the land. And further to the north is actually the Central Valley of California, and there's little patches of this is a major agricultural region, and there's areas of low coherence here, which are in some cases places where the farmers have plowed their fields. If a farmer plows his fields, he completely changes the surface, and that causes low coherence. And that can also give you a loss of coherence. And this big sort of triangular area is the Mojave Desert, which has a lot of sand. So that also has generally a lower coherence than the more rock areas around it. There's this funny blob of weird phase here. That's actually caused by radio frequency interference that's present. There's actually a Federal Aviation Administration, FAA, radar system there, and it causes interference with the NISAR data. That's present in these older scenes, but we've now implemented a filter that removes this interference, and you won't see that in the release data that's being released in July. And that's an overview of how we can work with the actual data of the GONW files in a GIS. And I think that's a good place to end up here. Thank you.
Thank you very much, Dr. Fielding, for that great presentation and demonstration. Now I will do a summary of today's session as well as the previous two sessions. So this is a summary of today's session. InSAR measures distance from the satellite to the ground with high precision by using the phase of the reflected radar signals. The coherence of the InSAR phase is a measure of surface or surface cover stability at the radar wavelength scale. And phase cycles in a repeat pass interferogram show change in distance to the ground by half the radar wavelength. That's 12 centimeters for NISAR. The NISAR InSAR products enable user analysis of interferograms with few additional steps. And the NISAR InSAR measurements of surface motion are useful for a variety of geological processes, some hydrological processes, dynamics of glaciers, and other effects that displace the surface or large structures. The NISAR GUNW interferometric product is geocoded and is the best suited product for users that are new to InSAR. And here's the summary for the second session. NISAR data are freely and openly available. The L-band data can be accessed through the Alaska Satellite Facility, while the S-band data, along with coincident L-band data, are available through ISRO's Boonity platform. L-band provides near global coverage every 12 days, whereas S-band observations are acquired primarily over India and selected science and calibration validation sites outside India. NISAR data are distributed in HDF5 formats. The level 2 NISAR products are geocoded, allowing them to be readily overlaid with other geospatial data sets. There are Jupyter notebooks. These are open source notebooks that contain algorithms for the mission's different science disciplines, and these notebooks are publicly available. The only Global 3 product generated by NISAR is soil moisture, which has a spatial resolution of 200 meters. The GCOV product is the geocoded, geometrically terrain-corrected backscatter data in gamma naught, and it's the most suited for those new to radar and wanting to do ecosystem type studies. So for example, deforestation, biomass, agriculture, flooding, etc. The GUNW product is a geocoded wrapped and unwrapped interferogram, and it is the best suited data set for those new to InSAR and wanting to do surface deformation or movement type studies. And finally, NISAR data can either be downloaded for local analysis or accessed and processed in the cloud, depending on your workflow. And this is the summary from session 1. NISAR is designed to monitor continuous Earth surface changes from the order of centimeter to meter scale, globally, day and night, and through almost all weather cloud conditions. The key focus processes include tectonic deformation, ice sheet motion, ecosystem change, and agricultural monitoring. NISAR has an L-band sensor at 24 centimeter wavelength and an S-band sensor operating at 9.4 centimeter wavelength. The satellite has an exact 12-day repeat cycle and an imaging swath of about 240 kilometers. The spatial resolutions vary between 3 and 30 meters depending on the radar acquisition mode. Polarization acquisitions vary depending on the acquisition mode. The core science disciplines cover the cryosphere, ecosystems, and solid Earth. And NISAR can also address different applications and support disaster and hazard management. Data processing levels span from level 0, which is the raw data, to level 3, which is a geocoded derived product, with soil moisture, as mentioned already, being the only level 3 global product being generated. Level 1 and Level 2 products contain information about amplitude, phase, interferometric products, coherence, and pixel offsets. The Level 1 are in radar coordinates, range Doppler, and Level 2 products are geocoded and analysis ready. In July 2026, the fully calibrated forward process data will be released with a data availability latency of 36 to 72 hours. As a reminder, there is a homework assignment. You can access the homework through the training webpage as of today. The answers must be submitted via the Google Forms, and the due date is August 6. A certificate of completion will be provided to those that attended all three live webinars. The attendance is recorded automatically, and complete the homework assignment by the deadline. The certificate of completion will be emailed approximately 2 months after today. I'd like to thank all of our guest instructors for this training series, Dr. Franz Meyer from the University of Alaska Fairbanks and the Alaska Satellite Facility, Heidi Christensen from the Alaska Satellite Facility as well, Anupama Sharma from the National Remote Sensing Center from ISRO, the Indian Space Research Organization, and finally Dr. Eric Fielding from JPL. And of course, if you have any questions about the material that was presented today, please don't hesitate to contact Dr. Eric Fielding through the email that you see here. So please share your thoughts. Before I close, I just wanted to remind you that within a day or two, you'll be receiving an invitation to complete a short online survey. And this feedback will help us improve the ARSET program. The participation is optional and all responses are confidential. But the survey data is really critical to help us understand how to better meet your needs. So we want to help you use Earth observation data more effectively, but we need your feedback. So please share your thoughts. And with that, we've reached the end of today's session, session number 3, and the end of this training series. So I'd like to thank Dr. Eric Fielding for the great presentation today, and we will now begin our question and answer session. Great. And yes, thank you for all of the great questions that have been coming in. We've been compiling those, and we'll be sharing that document here on screen. But just to remind everyone that please, there are 3 sessions as part of this training, and please feel free to contact either me or any of our guest speakers whose emails we posted for each session. And as a heads up, so this is an introduction to NISAR training, and we are planning several trainings that use NISAR data throughout the next year. So please keep tuned into what's coming next. All right, so we do have Dr. Fielding is here. He has been answering the questions that have been coming in, and we'll try to get through as many questions as we have time. If we don't get through all of the questions, we will be posting this document on the training webpage with all of the questions answered. Okay, so let's get started. Question number 1. I need to know if it's possible to measure the height of a crop, for example, corn or soybeans, using radar technology. And what characteristics should the radar have to achieve a result with an acceptable margin of error? Go ahead, Dr. Fielding.
NISAR InSAR is not particularly sensitive to crop height because it's L-band, and especially for relatively small crops like corn or soybeans, the radar is going to be going through and mostly bouncing off the ground. If you want to measure crop height, you probably want to use radar with a shorter radar wavelength, like X-band, where the crop height would be more have a bigger effect on the interferometric phase. In addition, to really get a good measurement of height of crops, you would want to have different a larger baseline. NISAR is designed to fly with the satellite keeping the orbit small and all the baselines small, so the effects of height, of vegetation height, are going to be less for trying to with the interferometric effects.
Great, thank you. Question number 2. I've been trying to download a gcov NISAR file from ASF Vertex, but each time the download completes, it restarts instead of finishing. So what could this be? And the answer to that is we have forwarded this question to the Alaska Satellite Facility team, and we will post a response to this here. It could be the server you're using, but we will be responding to that. Sorry, the browser that you're using. All right, so the next question, number 3, can NISAR InSAR time series be used to detect glacier surface deformation or glacier velocity changes? And are there any planned applications for monitoring glacial instability or glacier lake outburst flood hazards? Go ahead, Dr. Feeling.
Yes, the InSAR time series it can be used to measure glacier surface velocities. That is one of the main applications of NISAR. I'm on the solid Earth part of the science team, but we have several people in the cryosphere part of the science team that are using NISAR InSAR data to measure glacier velocities, both in mountain glaciers and in the large ice sheets. The cryosphere people also use pixel offset tracking to measure the glacier velocities where the velocities are larger. And one of the examples is this It's Live project that's highlighted here. That uses pixel offset tracking on the radar amplitude images, both from NISAR, Sentinel-1, Landsat, Sentinel-2, to get a complete picture of what the velocities are for the faster moving glaciers. But the InSAR is good for the parts of the glaciers that are moving more slowly. So it's really depending on how fast the glaciers are moving, which technique you need to use. InSAR can be used to see if the glacier is speeding up or slowing down with time, and that can be possibly helpful for looking at glacier lake outburst flood hazards.
Great, thank you. Let's go on to then question number 4. Has NASA evaluated integrating NISAR InSAR deformation measurements with machine learning models to predict landslides or glacier-related hazards in high mountain environments? And what are the main challenges?
Well, we don't yet have enough NISAR InSAR data to do machine learning analysis, but scientists have done machine learning analysis with InSAR data from other satellites. One of the main challenges of applying machine learning models is that many existing machine learning models use either the time series of each pixel or the spatial distribution of pixel values, which are displacements for InSAR, from a single image. The machine learning needs to consider both the spatial distribution of displacements and the time history at the same time, and that may require more advanced machine learning models to be able to handle that type of really three-dimensional information of both 2 dimensions of spatial distribution and 1 dimension of time history.
Great. Question number 5, how do we map urban flooding? And I'll take that one because for that you need the GCOV, the amplitude data. And in fact, InSAR is not useful for mapping surface water extent, whether it's open water or inundated vegetation. So the plan in terms of ARSET trainings is for actually the next training to be focused on mapping floods. So do keep tuned. The next question, number 6, what are some other phase unwrapping algorithms other than SNAFU?
So the standard algorithm that's used by ICE for the NISAR processing is SNAFU, but there are the ICE3 software package that NISAR mission uses for processing does have other unwrapping algorithms included in the software. So it is possible if you want to do your own processing with ICE3 to use those other options. And there's also commercial packages such as Gamma that can process NISAR data with their own phase unwrapping methods. There are a few examples here. There's called Spurt and Whirlwind. The NISAR processing system may be moving to one of these other packages in the future, but at the moment, the present software is using SNAFU as a standard for the standard products. The Opera project uses a different phase unwrapping, and they will be producing displacement products from NISAR for North America within a year or so.
Great, thank you. Let's move on then to the next question, number 7. How does SAR and INSAR differ relating information about forests, their canopy size and chlorophyll content, and how does one try to correlate water resources in a nearby environment with inundated or non-inundated areas? Okay, so this question has multiple parts. I'll answer part of it in that chlorophyll content, for that you need to use optical, right? Because radar is not going to be sensitive to the chemical properties of the vegetation. However, as posted here, there have been attempts to estimate NDVI from SAR with deep learning techniques, and there's a link to that paper here. But go ahead, Dr. Fielding, if you want to respond to the rest of this.
Yeah, the INSAR is not going to tell you anything about the chlorophyll content. It's only seeing the physical structure of the forest. So it can have some some effect due to the volumetric scattering in forests. So that's somehow related to the biomass. But the NISAR biomass estimates are made from the the amplitude images, the GCOVs. So the standard NISAR biomass products are not using INSAR.
Great. Then let's move on to the next question, which is question number 8. How effectively does NISAR L-band retain coherence over Korea's forested and mountainous terrain?
I think one of the ASF people did this search and pasted in the search URL here, so you can go and look at the. There are a few scenes from the February release already online that you can look at the coherence layer and see what the coherence is for those areas. And in fact, we have looked at a number of forested areas around the world, and the coherence is much, much better than with any C-band radar, especially because of the 12-day repeat time and high spatial resolution of NISAR.
Wonderful. Okay, question number 9. Will NISAR products be available in Indonesia?
Yes, the global forward processing that's going to be released later this month, or expected to be released later this month, will include global coverage. So it will include Indonesia and the whole rest of the land area of the Earth.
Great. Question number 10. My intention is to learn how NISAR can be applied for landslide early warning in extreme weather events.
So NISAR is not going to be useful for early warning of landslides caused by extreme weather events. The NISAR InSAR coherence and amplitude images can be used to map the extensive landslides after they have occurred, but NISAR does not have any way to provide real-time precipitation estimates that would be necessary for early warning of landslides during an event. NISAR does have the soil moisture estimates that we haven't really talked about so much in these trainings, but there's the 200-meter soil moisture estimates, and that can measure what the soil moisture is before the event, and that could be combined with some precipitation estimates to better predict where landslides might occur during the extreme weather.
Good. Okay, the next question and oh, by the way, before I move on, yes, in terms of future trainings, we will be doing one on the soil moisture product as well, sometime within the next year and a half. All right, the next question is number 11. What are the recommended best practices or threshold values for using the coherent band to mask out severe phase noise?
The exact relationship between the coherence measurement, the numbers, and phase noise depends on the number of looks used in the processing and the way that coherence is estimated. With NISAR data, typically areas with coherence less than 0.2 is completely decorrelated, so that would be like water surfaces. And in many cases, coherence less than 0.4 is getting to be too noisy for accurate phase unwrapping and displacement measurements. So that's typically the threshold that I would use for masking out unreliable phase and displacement measurements.
Good. Along those lines, on landslides number 12, how effective is InSAR for rapidly moving landslides where coherence is quickly lost? And are there alternative processing strategies for such events?
So the L-band radar wavelength of NISAR is able to keep coherence for landslides that are moving up to 1 centimeter per day, roughly. The Palos Verdes landslide example that I showed you is presently moving around 1 centimeter per day and still keeps coherence. If it's moving faster than that, then you need to use the pixel offset measurements. The standard NISAR processing to the geocoded offset products is only done in cryosphere areas. So you would have to do your own pixel offset measurements with the NISAR data to measure the faster landslides moving faster than 1 centimeter per day. But 1 centimeter per day is really unusual for landslides.
Okay, great. The next one, what are the opportunities, question number 13, the opportunities and limitations of using NISAR InSAR for long-term wetland hydrology monitoring?
NISAR wetland extent is typically measured with the NISAR amplitude images, the G-coves, not with the InSAR. But INSAR data has been used to measure the surface um, in flooded vegetation because with the double bounce of the radar, you can often get coherent reflection returns, and the phase of that return will depend on the height of the water in flooded wetlands. So that's a technique that's been used in a few places. In most cases, if it's not full of vegetation, then the coherence will be zero, and you can't use INSAR phase.
Okay, the next question, number 14. Can we use NISAR for infrastructure monitoring, like airways? I guess airports.
Airports, yes. Yes, INSAR and NISAR in general can be used for monitoring surface displacements of a wide variety of infrastructure things, levees, dams, roads, bridges, pipelines, airports, and other features. And so it's very useful for monitoring infrastructure. The L-band radar wavelength is going to give you better coherence in places where there's vegetation. The L-band radar wavelength actually does not work so well for the extremely smooth surfaces in most airports. And you may have seen in that in my example of the Los Angeles area that the areas of the runways of LAX were very dark and incoherent, and that's because the smooth surface of the radar of the runways and the adjacent closely cut grass does not reflect the radar back, so there's very low signal, and we can't really get a good INSAR measurement. So you probably for monitoring airports, you might want to use a shorter radar wavelength.
Great. The next question, the question number 15. With NISAR dual pol, how should the effects of the ionosphere be taken into account? For instance, how should we address errors arising from channel mixing caused by the Faraday rotation?
Yeah. Since most of the NISAR data is only collected with two polarizations, it's very difficult to correct the Faraday rotation. You wouldn't be able to do that directly from the data, but because NISAR acquisition times are at 6 a.m. and 6 p.m. Local time, the Faraday rotation is probably going to be small in most cases.
Okay. Question. Oh, go ahead. Was there anything else?
No.
Yeah. Okay. And the next question, number 16. The NISAR products have been discussed in previous sessions. Is there a document available for S-band or dual wavelength L and S-band products?
Yeah, so there's a link here to the ISRO data product specification for the S-band data products, but the S-band data products have the same format and layers as the L-band products, including GONW. So the presentations we have here apply to the S-band data as well. It's just that you have to get the S-band data from ISRO and not from the NASA repositories.
Great. The next question, let's see, question number 17. How does NISAR's L-band improve temporal decorrelation when compared to Sentinel's 1 C-band? What are the limitations of L-band?
So the big advantage of L-band is that it's less sensitive to vegetation. Basically, For moderate to, and low levels of vegetation, the radar goes all the way to the ground. For denser forests, the radar is going to be bouncing off the trunks of the trees and maybe some of the larger branches, and not the smaller leaves and small branches that move around. So um, the coherence is much better with L-band, both over time and even just for a single short interval. In fact, in a few places where they did the special Sentinel-1 one-day repeat last month, where they had the Sentinel-1A and Sentinel-1C collecting data only one day apart, the NISAR L-band coherence is generally better over with a 12-day NISAR L-band interferogram than with the one-day C-band interferogram from Sentinel-1. And of course, that was only a temporary experiment that they did during June of 2025. So the regular C-band time interval operationally is 6 days when they have both the two satellites working and acquiring data, like now with Sentinel-1C and Sentinel-1D. Sentinel-1A has now been decommissioned after that short experiment in June. The main limitation of L-band is the ionospheric effects are stronger, so you need to do the ionospheric phase correction, but NISAR has the extra L-band frequency band. We didn't really talk about that in detail, but it gives us a much more accurate estimate of the ionospheric phase screen that you can use to correct the ionospheric effects.
Okay, great. The next question, number 18. What is the strategy for resampling 80-meter unwrapped phase from wrapped phase at 20 meters?
In the production process, the 20-meter interferogram is then multi-looked to about 80-meter pixels before doing the phase unwrapping with the SNAFU program.
Okay, so we have a couple minutes left, so I'm going to select a couple of questions down the list. So let's go to question number 21. How does the selection of a stable reference point differ between earthquake-related crustal deformation analysis and landslide displacement monitoring, considering their distinct spatial scales, deformation mechanisms, and temporal characteristics? Choosing a stable reference point is very important for deformation.
Yes, of course, the reference point is very important. For landslides, we typically choose a reference point very close to the landslide because the landslide only affects a small area. So there's usually an area nearby that's stable that we can choose the reference point. For earthquakes or deformation for volcanic eruptions, the displacements extend over a much larger area. So then the reference point needs to be chosen far away enough that you can assume that the deformation is near zero.
Great. Then let's go to question number 23. In the last NISAR data release in February, there was a warning about ionospheric contributions not being completely removed. Have there been any changes in the ionospheric and tropospheric models to remove the contribution of these errors? And where can one find more details?
The ICE3 software is on the public GitHub. You can go to the ICE3 GitHub and see lists of what what was changed in the different versions of the software. The version that we're using for the release this month is ICE 3 version 5.02.3, which is then converted to this composite release ID P0523 that's going to be used for the release that's going to be later this month. One of the big, there's been a number of improvements to the ionospheric estimate. As I mentioned, one of the improvements was to mask out areas of low coherence and interpolate to get a better estimate in areas of low coherence within a scene. Another big improvement is that the new version has filtering of radio frequency interference that caused errors in the ionospheric estimates with software used in the February release. And there's a number of other improvements that have been made to the ionospheric estimates. I think the tropospheric correction layers are approximately the same in the new version as in the February release, but the ionospheric corrections are considerably improved. So when you get your data, you want to look at this, the CRID or composite release ID, and make sure that you're getting the new data, whether it's P05023, as opposed to the old February release, which is CRID X05010. Which is the old software.
Great. Let's go then to question number 27. Are the available GUNWs always only between the 12-day return pairs? Will different temporal baseline interferograms need to be processed separately if we want them? So for example, when working with Sentinel data, I've used pairs with a longer temporal baseline.
Yes, the NISAR GUNWs are only produced from the nearest neighbor in time pairs. If you want to get interferograms with different time intervals, you would need to do your own interferogram processing from either the geocoded SLCs or the range Doppler SLCs to make your own interferograms for different temporal baselines.
Great. And then one more question. Let's go to question number 40. Can you expand a little more on coherence? What is the difference between temporal and spatial coherence? You mentioned that coherence has multiplicative components. Are these for temporal or spatial? And how do you evaluate them?
Yeah, temporal coherence is derived from time series analysis. So it's different from the spatial coherence that we used for many years, and the coherence layer in GUNW files is a spatial coherence. The multiplicative nature of coherence applies to both temporal and spatial coherence. So it's basically anything that makes the coherence low will make the temporal coherence low and the spatial coherence low. So the estimation of temporal coherence is a more advanced topic that we didn't cover here, but there's going to be other trainings in the future that talk about that.
Great. And how about we do one more? I always like the Q&A sessions, and if we had time, we would go through all of them. I know that we're over our time, but let's just do one more question. So how about we go to question number 44. So I would like to know the typical baseline separation associated with the 12-day repeat past NISAR acquisitions and its expected impact on coherence over forested areas.
The NISAR baselines, perpendicular baseline separation, are almost always under 150 meters and typically only on the order of 50 to 100 meters. So this means that um, the spatial baseline effects on correlation or coherence are quite a bit smaller than the temporal decorrelation effects due to random motion of the forest uh, branches, and even at L band, there's some amount of temporal decorrelation.
Great. Okay, so as mentioned, we have a lot of questions here. We have over 50 questions. We will be answering all of your questions in this Google Doc, and then we will be posting it on the training webpage. So don't forget the homework. You can access it as of today. And also, please, if you can make sure you complete the survey, it helps us a lot for future trainings. Before I close, I'd like to thank the ARSET team for their incredible effort in putting this together. Block Blevins, Natasha Johnson Griffin, Selwyn Hudson Adoy, Jonathan O'Brien, Sue Monty. There's a whole team behind all of this, Sherry Morris. And I'd like to thank our incredible guest instructors, Dr. Franz Meyer, Heidi Christensen, Anupama Sharma, and today, Dr. Eric Fielding. Before I close, I'd like to provide the opportunity for our guest instructors to give some final words. Dr. Eric Fielding, would you like to say some closing words?
Yes, I also thank the ARSET team for all the work they did to get this to make this webinar function smoothly and help to keep the whole training system convenient for me to do the webinar and be effective for the users.
Thank you very much, Dr. Fielding. It's been such a pleasure and an honor to have you here with us again, teaching us about INSAR and specifically now INSAR related to NISAR. So before I close, I'd like to thank the help from the Alaska Satellite Facility that we had today. 2 members from the ASF joined us today to support with questions. So I'd like to thank Alex and Zachary. So Alex Lewandowski and Zachary Hopinen. And yes, so this is the end of this session, but hopefully it's at this training, but hopefully the beginning for you to start working with NISAR data. Please, we want you to work with the data. We want to hear from the community in terms of what are the challenges. So please reach out to us, to any of the instructors, if you have questions. And more will be coming, as mentioned, more trainings will be coming in the near future. So thank you to all of you, to all of the participants, really for your interest and your enthusiasm for this amazing mission. And until next time, have a great day, everyone. Bye-bye.